Well, good afternoon, ladies and gentlemen, and welcome to the 10th Andrew Chamblin Memorial Lecture. My name's Nigel Peake, and I'm head of the Department of Applied Mathematics and Theoretical Physics here in Cambridge, and it's our great pleasure to be able to host this event. So first some words about Andrew Chamblin, and then some words about today's speaker. Andrew Chamblin was born in Lubbock, Texas in 1969. After a brilliant physics undergraduate career at Rice University, he studied twistor theory in Oxford with Sir Roger Penrose for a year before making a wise move of coming to Cambridge, to St John's College in particular, to study for his PhD supervised by my colleagues Stephen Hawking and Gary Gibbons in Department of Applied Mathematics and Theoretical Physics, otherwise known as DAMT. His thesis was entitled Aspects of Topology in Classical and Quantum Gravity. He then held a very distinguished Draper's Research Fellowship at Pembroke College here in Cambridge, followed by further research positions across the UK and the US, before becoming assistant professor at the University of Louisville. He died suddenly and unexpectedly on the 6th of February 2006 at the tragically young age of 36 and at the height of his academic powers. Andrew's family and numerous friends and colleagues worldwide came together to create this annual lecture and an annual organ recital in Oxford to honour his memory. My department is hugely proud of Andrew, and we are honoured to be able to stage this lecture each year. We've always been able to attract one of the world's leading theoretical physicists to give the Andrew Chamblin Lecture, and this year is no exception. Professor Raymond Laflamme is Executive Director of the Institute for Quantum Computing at the University of Waterloo in Canada. As it happens, Ray also completed his PhD in DAMT, supervised by Stephen Hawking, and he's made many important contributions, including work on the direction of the arrow of time in a contracting universe and the discovery of the famous Gregory Laflamme instability in string theory. Since the mid-1990s, he's conducted seminal research on quantum computation and information, which is the subject of today's lecture. So, Ray, we were delighted that you accepted our invitation, and we're very much looking forward to your lecture. Thank you.
Thank you very much, Professor Peake. Thank you very much to the Andrew Chamblin Memorial Lecture Committee who has chosen me to come and give this lecture today. Thank you to the Cambridge Science Festival to host this lecture, to Gary Gibbons who sent me an email about 6 months ago to invite me, and to Malcolm Perry for taking care of part of the logistics to have me here. It's an honor to be here, and I must admit that Andrew Chamblin and I did not overlap while I was a student and then a research fellow at a time, but we had some interest in common. And Professor Peake mentioned the work on the instability of black holes in 5 and higher dimension. And I remember Andrew and I at many conferences talking about this, and although me and Ruth had done the calculation, he was very much interested in the implication of what that meant for the universe in which we live. But around the 1990s, I got distracted and started to work in something which is different than gravity, which was what Andrew loved and worked on. I started to be interested in the use of quantum mechanics to manipulate information. And I started more and more to work in that direction. And today's lecture is not only theoretical, but also experimental, as I went down and down this path of going down to more practical things and even dirtying my hands at doing experiments. I'll hear a little bit about them a bit later on. But to start with, really at the foundation of quantum information science is a place about interference. And what I mean about interference is not what we see between here and DAMT in the fields where people play different types of sport, but this type of interference of single quantum systems. In the world in which we live and then we grow up, we believe that objects are at a single place at a given time. But when we go to small systems, we realize that the laws of physics changes. And this is what this lecture is about, is to use these properties of nature, try to harness them, to make them something for us. But before I go down there, I should really go back and explain why do we do that work. And really, it starts with curiosity. Fundamentally, we're all curious. I assume if I ask you this question, you probably answer, yes, we are curious. The fact that you're here today is testimony to this. But if I ask the question, why are you curious? What would you answer? Nobody has an answer? So why are we curious? I think at the end it's Darwin's principle. Because humans have realized that by focusing our curiosity in certain areas, physicists like me realize that we can start to understand some phenomena of nature. And when we can understand some phenomena of nature, we can start to predict how they behave in different circumstances. And when we can understand how to predict them, we start to understand how to control them. And when we control them, then we use them to do things that we're not good at or that we cannot do. And these things we call technology. And then some of these technologies kind of have an impact on society. Things makes us do things which we would have never expected. And another impact of these technologies is that it gives us some tools to go and explore the world at different scale, either big or small, and start this cycle and do it again and again and again. Example of this would be 20,000 years ago. Some humans being were looking at fire that would come mostly from lightning storms and forest fires. There were a few human beings who were crazy and bold enough to get near to that fire, realize that you can tame it, you can harness it, you can build a rock and use it. And 20,000 years ago, people realized that you could use it to melt metal and make tools, for example, for agriculture. And it is a time where humans change from being nomads to be more sedentary, and make small villages, because suddenly we can, with agriculture, make food which would last longer, so we didn't have to go hunting every day. We didn't have to move as much. So in this, really changed the fabric of society. Another example could be steam. About 300 years ago, people were still looking at fires and pots boiling and this thing coming out of it, and you realize that by putting a top on this cauldron, a little pipe, we can kind of use that steam, make it do something for us. We can build steam engine who allows us to go and get natural resources much further. And suddenly villages turned into towns. And then again, changed the fabric of society and led to the Industrial Revolution. About 100 years ago, same thing happened with electricity and magnetism, two forces which we thought were completely disparate. But suddenly they were the same forces once we put the mathematics together, and this mathematics predicted some waves. And then suddenly we learned how to communicate at long distance. And now we don't care about cities, really, about communication. We have the rest of the world at our fingertips. All these examples are from the past. And we can ask, what is next? What will be the properties of nature that we can harness in the 21st century, which have the potential of changing the world of technology? Well, you would be not surprised with the title of my presentation, that a combination of information theory and quantum mechanics. Bring things together, lead to quantum information science. Information theory has really changed our society in the last 50 years. Things that we thought were totally unimaginable. Going to the corner of the street and putting your little card and getting money that comes out. I had a daughter who was in Tanzania during the summer. She was living pretty much in a little concrete hut. But with the cellular phone, we could communicate kind of every day, nearly instantly. So the way we communicate has changed not only the way we work, the way the economy works, but I think essentially who we are. There's a second theory that kind of has had quite an impact on society in the last 50 years, is quantum mechanics. About 100 years ago, people realized that the laws of Newton, and maybe it is a challenge of saying this in Cambridge, the laws of Newton broke down. We couldn't explain certain phenomena. We couldn't explain the fact that in an oven, the element turns red, and with the laws of Newton and electricity and magnetism, we couldn't predict why it is red. We couldn't explain how electrons are emitted out of metals when we shine light on them. We couldn't understand why atoms are stable. A new theory had to be discovered. That was quantum mechanics in the early 1920s. This has led to some interesting technology, harnessing one piece of quantum mechanics, the fact that we can tunnel through barriers, something which is impossible classically, potentially. The fact that energy doesn't come continuously, but in chunks, as we see from particles of light or photons. This led to technologies like magnetic resonance imaging, like the laser, or even the transistor. If you turn quantum mechanics off, transistor would not work. We would not have the computers that we have. But it used only a small part of quantum mechanics. And there's other properties of quantum mechanics that comes in, called the superposition principle. The equations of quantum mechanics are linear. If you have a solution A, a solution B, A plus B is also a solution. Mathematically, it's very simple. But what does it mean physically? That we can be here or there at the same time, or here and there at the same time? And the answer is yes, quantum system can be at two places at the same time. And how do we know this? We know this by looking at experiments that'll come back. There's another principle of quantum mechanics that we don't seem to have been used before, the uncertainty principle. The fact that we cannot know the position and the momentum or the velocity of a particle at the same time. It seems to stop us to learn more things. But what we learn in a few minutes is that we can do things with this property that we couldn't do in the classical world. So let's get back to the superposition principle. Where does that come from, and how do we know about it? So we know about it about a very famous experiments in physics, dating to 1806, called the double slit experiment. We take a laser, like the one that is in my hand, we shine light towards two little slits, and we look at the screen. What does it look like? So what you can do is close one slit to start with, and you look at the pattern, and what you see is the pattern in green up there. If you close that slit and open this one instead, you see the same pattern, but just translated a little bit down. And the question is, what would you see if you open both slits? And your first guess would, you add these two patterns. But this is not what you see. You see something which is a lot more jagged, something which has more zeros of intensity. And if you do the experiments in real, you'll get something which looks like this. So you see the intensity goes up and down, and you have a black spot which correspond to the zeros of this intensity pattern. There's an easy way to understand this. It's to think of light being a wave. It goes through the two slits, and there is an interference that happens between the crest and the trough of the wave. And when they are topping each other, they cancel. And that's how we see the interference pattern coming here. It is the fact that there's two waves, some part kind of cancel each other, and that adds up to zero intensity. When the two waves, the crests are on top of each other, you see the maximum. Or if the two troughs are the same place, you get also maximum part. So that was very nice, and we could understand this until a troublemaker came in, looked at quantum mechanics, looked at properties of light, and realized that it cannot always be explained using the wave idea. When we send photons on a piece of metal, you really have to think of photons, particles of light, as little particles. So you can try to do the same experiment when we have very low intensity of light. As you go to very low intensity, light becomes granular. It comes in chunks, as I mentioned, photons. A little bit like if you would think of water. Now, water looks very smooth when you're very far from the surface, but if you go to the nanoscales, you'll start to see atoms and molecules in there. Photons are, in some sense, atoms or molecules of light. And so you can do the same experiment, and you block one slit, and you see what it looks like. As you send one photon, you don't know exactly where it was going to happen on the screen, but you send one after the other in such a way that you never have more than one photon in the apparatus. And you see the pattern here gets recreated. If you block this one, open this one, you see the same pattern. And the interesting question is what happened when you have open both. And what you see is, initially, it looks like it's random, but suddenly there's a pattern which appears. And the pattern does not correspond to the sum of those, but again, the term where we have interference. So a single particle of light seems to go through both slits at the same time, which is the superposition principle in action. So we cannot think about these particles as the particles of billiard balls that we have around, but they have this interesting property of being at two places at the same time. And it is this property that quantum information science is using. In some sense, we can think about this as the zero of one of our bits of information in our computer. This one is the one. And then we can be in 0 and 1 at the same time. And just changing the or for the n turns out to be an incredibly powerful tool that we can have when we use quantum mechanics. Now, one thing that is going to be challenging when we do quantum computing is that these zeros and one are never totally isolated from the rest of the world. And so there is noise that comes in. And one way of understanding the effect of the noise is to make these little slits and make them shake a little bit. And if you make them shake a little bit, and you add this pattern, which is change a little bit up and down, the interference terms disappear. And what you see reappearing is the sum of these two terms. This is how quantum information turns back to classical information. When you have systems which are not isolated, noise destroys the quantum interference. The quantum advantage goes away. I'm going to give you a first example of how you can use the superposition principle. It is a small game. It's a game where if you're classical, you will win only 50% of the time. But if you're quantum, you can win 100% of the time. So we have a Canadian coin. And I chose that one because it's the only one where you have the queen with a bear behind. So the trick of the game is you choose head or tail. And then you take it on one place, and somebody's going to flip it or not flip it. So you take the coin, and then you have to make the guess. So what do you get? Well, if you would answer, and instead of being quiet, you would 50% of the people roughly would get tail, and 50% would get head. So 50% of the time you would lose, 50% you would win. So let's try to do the game again, but quantum mechanically. So we're going to use quantum bits instead of the classical bits. And we can put these quantum bits in superposition. So the zero of my quantum bit, the tail, is like pointing up on that vector. The tail, the head, pointing down is the head. In classical mechanics, you can be either in that state or in that state. In quantum mechanics, we'll be able to use the superposition. The operation that we do is the flip. It's like a rotation around the y-axis to go from one state to the other. And what we're going to do is take a quantum bit. You show me what is the state that you started with. And me, when I receive it, I'm going to put in a superposition of 0 and 1 of the tail and the head. Now you decide if you're going to flip it around the y-axis or not. around the x-axis. So you can do it, or you cannot do it. So if I don't do a flip, I end up with a superposition of the tail and the head, the 0 plus 1. If you do it, the tail becomes the head becomes the tail. You haven't changed that state. So then, once you've done your operation, you give it back to me, and I undo what I had done before, and I always end up with the tail. And I will always win, because I will know what it is. This is a very simple game, where you can see that being on superposition, you can have a small advantage. You might say, I'm cheating because the state of the system can be different, but I can tell you, let's generalize this and try to take advantage of this. So this is your first quantum algorithm that you've learned, Quantum Algorithm 101. So when you come back up here, at your nice dinner party, you can show that trick of saying that you know quantum computing. The next step is quantum chess, a generalization of this. But to really understand quantum chess, then you have to Google that part. So that'll be a little bit more complicated, and it will take more than the time that I've allocated. So go and look at quantum chess. In fact, there's a specialist of quantum chess in the audience tonight. And I'll leave it to him to do this. Now what I would like to do is to give you an idea of why these superpositions are powerful. And it is a simple fact that if you have a single quantum system, I mentioned you can be in two states, 0 or 1, or you can be in 0 and 1 at the same time. So to describe one quantum bit, you need to describe how much of 0 you have, how much of 1. The example I gave you, we had exactly the same amount of 0s and 1, but in general you can have a quarter of 0 and 3/4 of 1, or you can have some number so that it adds up p, probability of being in 1, and 1 minus p to be in 0. So you can have any state which corresponds to the surface of that sphere that I mentioned a few minutes ago. If you have two quantum bits, you can be in 0, 0, and 0, 1, and 1, 0, and 1, 1, and you can be in superposition of these 4 states. So you'll have to give me 4 numbers to describe this. If you have 3 of them, you can be in 0, 0, 0, 0, 0, 1, up to 1, 1, 1. You'll have 8 numbers. So now it's pretty easy to figure out how many numbers you need as you add up. The largest quantum computing device that we have around today has about a dozen quantum bits. So to the power 12 is about 5,000. It's about 5 kilobits of information. When I go home and I tell my kids that we have a small quantum computer in the lab with 5 kilobits of memory, they laugh at me. They say, 5 kilobits? What do you do with this? I said, oh, okay, I'll work a little harder. In a few years, we'll have 20. So 2 to the power 20 is about 1 million. And they say, well, really? A megabyte? What do you do with a megabyte of information? So I said, okay, we'll work a little harder. We'll go to 30. 30 to the power 30 is gigabytes. They said, gigabytes? You get filled this up very, very quickly. So I'll work to 40. 40, we have terabytes. Then they start to take me seriously. When you have only 40 atoms, if you try to simulate this with classical devices and to follow where they're going, you would need terabytes of information to do this. If you go to 50, you go to petabyte. If you put most computers around the world, put them together, you barely have petabytes of data. So only 50 atoms gives you the power, computational power, that all computers put together can have. All classical computers in the world. So this exponential really gives you an incredible advantage. Now, with 50 quantum bits, there's no killer application that we have yet for that. We will do interesting physics experiments between 50 to 100. But to get interesting algorithm that will have societal impact, we need 1,000, 10,000 of quantum bits, and we'll come back to this in a few minutes. So what kind of things can we do? I mentioned physics simulation. So up to 30, 50 qubits, 100 qubits, 1,000 qubits, we'll do a very interesting summation of quantum systems, in particular related to condensed matter or material science, trying to design materials and try to understand it. The largest simulation that we have using classical computers with simulating the behavior of electrons is about 30 to 40 electrons when it's fully quantum. After that, we have to leave to some approximation. Then we're never sure how good these approximations are. Example of chemistry. We can think about other algorithms which are related to optimization. If we have a superposition of all these states, and suddenly some of these states are marked or kind of have a particular piece of information, turns out with quantum computers, we can find these marked objects much faster than we can do classically. There's application on cryptography and sensors, and I'll come back to those in a few minutes. So I will go back to what quantum computers are, what we need to build them, then mention quantum communication, where I'll go back to cryptography, and finish by telling you a little bit more about these quantum sensors. So how do we build a quantum computer? How do they work? What are the different parts that we need? So we need these quantum bits that I mentioned, but what are they? How do we put them together? Well, I'll give you an example of quantum bits in a second. So we want quantum bits, and we want to be able to, if we have 2, 3, 4 of them, we want to be able to have 10, 100, 1,000 of them. So we want to be able to scale the device. We need to be able to initialize them. If you don't know what is the initial state of your quantum system, you'll have garbage in and garbage out. So you need to be able to initialize them in a second, and I'll give you an example or two of how we do this. We need to be able to control its evolution. And the computer scientists have told us that if we talk to each of the qubits one by one, and if there's pretty much any type of interaction between their neighbors, between quantum bit 1 and quantum bit 2, and quantum bit 2 and quantum bit 3, and 3 and 4, then we can build any evolution, any program that you can think of, we can build them out of these simple operations. And then we need to be able to measure these quantum bits. So with these 4 steps, then we have a quantum computers. And at the end, we have to do this with a very small amount of noise. In fact, this is one of the things we thought was kind of the most damaging thing for quantum computer is the noise. And again, I'll come back to this in a second. But I want to add one little thing that quantum information science has brought us. When I learned quantum mechanics, when I did my PhD here on things related to quantum, we always went back to equivalent of Schrödinger equation, where we had to solve them. Quantum information science brings physicists with chemists, with engineers, and computer scientists. And one thing we've learned from the computer scientists is to think about the evolution of our system, not always by solving directly the equation, but by making what is called a quantum circuit, where time goes this way. And from this, you can see that I've left my role as a relativist, where time always goes vertical. And then I have my quantum bits on the vertical axis. And so I have my quantum bit 1, 2, and 3, up, 5. And these little boxes are these operations that we can do. So we can think visually about how we evolve our quantum system. And this has been incredibly powerful, because people have different ideas of how to build quantum computers. But this language is common to all of us. So if somebody finds a trick of how to make this piece more robust, it can easily be translated in other technologies. I mentioned about noise, and although I won't dwell too much about this, one of the big breakthroughs in the field of quantum information science is how to make quantum information robust. In the classical world, we've learned that there is error correction, that as your classical system evolves, by using not too many resources, and not too many means not going exponentially as the size of the problem you want to solve, you can make the information robust to noise. Up to the 1990s, people believed that there was no such analog for quantum system. In part because there's a theorem called the no-cloning theorem. You cannot copy quantum information. It's against the rules of quantum mechanics. And people thought that error correction was done by copying information. We thought the noise had to be discrete, and quantum mechanics has a continuous evolution. We thought that we could, in classical error correction, we have to measure the bits to take a majority. In quantum mechanics, if you measure, you perturb. It turns out that there was a workaround all these objections, and we were able to find a theory called quantum error correction, which can make information robust. And the cornerstone of this work is called the accuracy threshold theorem, which is that if the error rate is smaller than a value, which depends on the code that you're using, the type of noise, the technology, how the quantum bits evolve with each other, which is very technical. But the important is that there is a value of the noise for which that if you can do your experiments with a smaller amount of noise, you can use error correction and make your quantum system robust. So even if in the physical system it does not obey the pure quantum mechanical behavior, a small noise comes in to try to turn the system to a classical one, you can, with quantum error correction, protect the quantum information against these errors. So here's a list of devices. I mentioned quantum bits. Physically, what would they look like? So I'll use a few of them. Let's say ion trap. We take ions, ionized atoms, they all charge. We put them in a radio frequency trap that brings them together. The Coulomb force kind of put them apart. The radio frequency field that you put brings them so that you have a chain of them. You can take a laser and you can illuminate each of one separately and make the electron being from their ground state, you would call this a state 0, to an excited state 1, which is the one of your quantum information qubit. So with lasers, you can talk to each of the qubits separately. And then you can send a laser at a slightly different frequency so you can make them move or dance together. And once they dance together, you can make them interact with each other. And with these two operations, then you can build any kind of algorithm that you want. Another example is nuclear magnetic resonance. Atoms like hydrogen or carbon-13 have small magnets inside the nucleus. They point up, it's a 0. They point down, it's a 1. They can point this way, it looks like 0 plus 1. This way, it's 0 minus 1. And if they point towards me, it's 0 plus I1, with I being the square root of minus 1. So you can make superpositions of zeros and ones in there. The little magnets behave not that differently from the magnet on your fridge. If you put some next to each other, this one will increase the field that this one sees, and then make this one behave slightly differently. This dipole-dipole interaction can be used to make the two quantum bit gates that we need to do a generic operation. To put them in the initial state, you can go to low temperature. You can cool them down so that it's only all these nuclear spin or the electron spins point up. When we want to do this with ions, we shine lasers so that all the excited states go down to their ground states. This is where we start our computation. There's about half a dozen of these blueprints for quantum computers. And to show you that my unbiased view on them right now, I put them all in alphabetical order. Some of them have advantage that the other ones don't have. But what we've seen in the last 10 to 15 years is a steady increase of the number of quantum bits that can be manipulated. Here's a plot. Time from year 1995 to 2010, number of qubits from 1 to 14. So slowly coming up. And from that benchmark, having looked at the number of quantum bits, it has been a slow increase up to now. But where we have seen the increase is the error rate at which we can manipulate these devices. 10 years ago, if somebody would have done a really, really good experiments with a few quantum bits, the error rate were 10, 15%. And today they are 1 part in 10 to the 3, 1 part in 10 to the 4, 1 part to 10 to the 5. So the amount of control we've gained has been tremendous. And once we've built on this control, then we can go to the next step and build quantum computers with 50 to 100 qubits. So in these 4 technologies, ion trap, superconducting, qubits, atom traps, and nuclear spins or electron spins, there's 5 or 6 groups around the world, one in Oxford, one in Waterloo where I am, one at Santa Barbara with Google, one at IBM, who claims that they will have 100 qubits in 5 years. And this will be really kind of departing from this being physics experiments that you do in the universities to demonstrate that these things are possible, to turn to engineering, where you can bring devices which are becoming useful. And so the next 5 years, we will see a dramatic improvement in the number of qubits that are being evolved. Once we get to 100 quantum bits, we can use these small quantum computers to help us understand the control to go to 500 and 1,000 quantum bits and then leapfrog. I'm going to switch now to quantum communication. So what I've talked about is using these quantum bits to manipulate information to compute. What we're going to do now is to communicate information in one or the other. And so we're going to typically using photons, particle of light, sending to somebody, and then use it from one task to the other. And there's many tasks that the people in quantum information science have discovered. One which is called quantum teleportation, which is the ability of moving information from one location to another one using what is called entangled state, which allows you to move this information without having to go through the information in between. Only the correlation kind of gets translated from one place to the other. It's one of these things that sounds like magic. If you take the mathematics of quantum mechanics, it seems to be an obvious thing. But you go in a lab and you can see these things happening. There's something called quantum secret sharing, quantum digital signature related to cryptography. But what I want to focus in the next few minutes is what is called quantum key distribution. And the idea is to exchange a key for encoding information. This is something that we've seen quite a lot in the digital age. The ability of exchange a key so that we can encode your messages. Today's encryption turns out that relies on the difficulty of solving a mathematical problem. You might know that when you go on the web and you go to your bank or to a place where you want to buy something on the internet, the website HTTP gets transformed to HTTPS. S is for secure. And when this occurs, then your bank takes two prime numbers, 5 and 3, multiply them with each other, and send you 15. You get 15, and with this number 15, you can encode your information and send it back to your bank. Now, 15 is pretty easy to factor, and you do this in a snap. If I give you 4,021, it'll take you a little more. And if I give you a number with n digit, it goes like the exponential of the log of n. It becomes incredibly hard. And so with a 1,000-bit number that you want to factor, the time for most classical computers is much longer than when you want to preserve the information. This is what the encryption today works. And one of the applications of quantum computer turns out to be the ability of factoring numbers which are product of prime very easily. So when we have quantum computers, the information that we have spread through the internet, even encrypted, will become totally public. And it's a question of time. All the information you send through the internet, even encrypted, will be decrypted. Like that were a certain agency, GCHQ in Britain, the NSA in the US, Canada Security Establishment in Canada. And in fact, these agencies are worried enough that last fall, in August, they announced that they would not make a transformation to other types of cryptography until we know which one are quantum safe. So they have agreed, or they have kind of decided that quantum computing was enough of a threat that the future types of encryption that they will use had to be safe against quantum computers. So how does quantum key distribution, which is a way of making encryption safe against quantum computers? It comes from a form of cryptography called a Vernon cipher. We have a message in bits, of course, and then we have a key. Alice and Bob meet and exchange a key. So on Monday morning, you go to your bank and you get a set of keys that you are going to use, and you encrypt your message with the key just by looking at these two bits. If they are different, you put a 1. If they are the same, you put a 0. And with this, your encrypted message is as random as your key. And your key has to be a set of random sets of 0 and 1s. For anybody who doesn't know the key, your message will look totally random. Bob, on the other side, has the key. So he can take the encrypted message, he adds the key, and gets back the message that Alice has sent him. This is perfectly secure as long as these numbers are really random. The challenge with this in our daily life is that you would have to go to your bank every Monday morning to get a set of keys, and you cannot reuse the key. If you reuse the key, then suddenly statistically some messages will come out and you'll be able to decrypt some of those. In the classical world, on the internet, as I mentioned, instead of using random keys, what people do is that they use mathematical problems which are hard to solve. A mathematical problem which is hard to solve looks random for people who haven't solved it. So this is what has been the solution in the internet world, something that is under threat. So there's another way of doing this, and this is to use the uncertainty principle of quantum mechanics. In the classical world, you cannot send your key through the post because somebody can open the envelope and looking at what the key is, and you would never know. In fact, you know if you look at some spy novels that people were doing this in the past. They were looking at the messages that people sent. In the internet, people are tapping all the messages that you're sending. Google looks at all the messages that they can catch on. If you send a Gmail email address using a Gmail address, Google looks at all your messages, keep the information, and then they're going to use it at some point. In the quantum world, it turns out that because of the uncertainty principle, you can detect if somebody is eavesdropping. So the basic idea of quantum cryptography is to send a key and to sacrifice some element of the key to see if somebody has looked at it. And if somebody looks at it, it will change some zeros to a 1 and some 1s to 0. And so if there is no eavesdropper, there'll be no error rate. But if there is an eavesdropper, then suddenly you can find out that somebody has been looking because some piece of the key that you've sampled and exchanged with Bob openly kind of picks out the fact that the error rate has gone up, and then you say, somebody is eavesdropping. By exchanging a key, you have not exchanged the information yet. So if the key has been eavesdropped on, you just throw it in the garbage and you start again until you have no error rates. In fact, you don't need 0 error rate. You can show that the error rate has to be small. So this is really a reasonable thing when you want to go and do experiments. It turns out that it is simpler to build quantum key distribution systems than to build quantum computers. And we do have some of these systems around the world. Here's one that we have at the University of Waterloo. On top of one of the buildings at the university, we have a source of entangled photons. It sends photons, little red dots. If your eyes are really good, you would see them going through from one location to the other. Alice and Bob gets a key, and then they sample their key. They say, bit number 3, Alice, what did you get? Bit number 13, what did you get? Bit number 34, what did you get? And if you get an error rate that is high, then you know that there's been an eavesdropper. You throw away and you start again. People can do this on free space. They've done this between 2 of the Canary Islands, distance about 100 kilometers. People have done this with optic fibers in Japan and in Germany, in Austria, where we can send particles of light through optic fibers. We can go to about 100 kilometers until the photons have been observed. Now, if you know a little bit about fiber optics in the classical world, you know that there is a repeater around 20 to 30 kilometers. If you do this quantum mechanically, this is like an eavesdropper. So we can not use classical repeaters. So we have to use direct lines. So here's the big challenge for quantum key distribution. How do we do this? Go to the surface of the Earth. About 100 kilometers we can do, but if you get to London, there's these things called buildings, which are not very useful for the physics experiments. We'd have to do some weird things to kind of go around. Maybe optic fibers in a city is a way to do it. But if you want to go from London to Manchester, you would have to use something different. And what people have come up with is going through satellites. It turns out that if you go to a LEO satellite, which is about 800 kilometers above the surface of the Earth, the optical depth is the same as about 100 kilometers on the surface of the Earth because the air gets thinner and thinner and thinner. So then you can use satellites. And the basic idea is to have a satellite which sends 2 of these entangled photons, one to Manchester, one to London. And then once you get at each location, then you use optic fibers for local distribution. And these experiments are being done today. Although the satellite one has not been done, here's other experiments we've done at the University of Waterloo. It is between the top of a building and a car, or what we call in the US a pickup truck. So we send a pickup truck on a nearby road, which is about 1/4 of a kilometer. The road is nicely a semicircle, so we can align the back of the car with the top of this building, and then we can exchange a key between Alice on the top of the building and Bob kind of in the pickup truck. So because this is very sensitive to light around, as I mentioned, and noise, the students do this at night. They do this between about midnight and 5 in the morning when there's very low sunlight. One night the students are doing this, and they want to go at about 30 kilometers an hour, about 20 miles an hour, 20, 25 miles an hour, which is at this distance the same speed at which a satellite would go in the sky. So they are going this with a flasher on their car, and they get stopped by the police. So the police says, "What are you doing?" And the students come out, and they don't know exactly what to say. And he said, "Oh, we are trying to untangle Alice and Bob." And the police said, "You must be one of these quantum people." So the progress on quantum key distribution has been quite impressive in the last year, and I think in the next year or two, we will see communication between Earth and satellites. Once we show we can do this, the first experiments will be, of course, just proof of principle that this is possible. But from there, I think the idea of commercializing this technology is definitely going there. In the last few minutes, I want to go and talk about one last piece of technology, quantum sensors. And the basic idea behind this is once you start to think about quantum computing, quantum communication, quantum sensors, you can think about it globally as what we are developing is the right language, the right framework to talk to atoms and molecules and have them talk back to you. You have the right language, quantum mechanics makes them do something. We think about quantum sensors as a small device with a few quantum bits, or a few atoms around that you can manipulate so that they can extract a piece of information around that can be useful for one purpose or the other. So maybe we can say that not only we have physicists, chemists, engineers, and computer scientists and mathematicians doing quantum information, but maybe people in the arts should have a part also, and the linguistic people could have a contribution to quantum information science. With quantum information science, we will really go and achieve the greatest precision, sensitivity, selectivity, robustness, and efficiency that nature allows, as long as quantum mechanics being the fundamental theory of nature. I'm going to give you an example of how one particular sensor works. It's called a neutron interferometer. It uses neutrons as the particles, similar to photons. But photons, if you try to look at scales of about the nanometer, the wavelength of photons will be in the X-rays, and typically they would ionize your atoms and really, really disturb them. So if you want to have probe on a nanometer, you want to use different system. If you send neutron at a speed of about kilometer per second, their wavelength is about nanometer. And neutrons pass through matter very easily. But quantum mechanics tells you that neutrons can be thought as particles, but they can also be thought as wave, like photons. And so here's an interferometer, and here's the real-life version of it, something which is as big as my hand. Neutrons would come in, in the part here, and then they go to this first beam splitter that will take the beam of neutrons that comes one by one, split them in two, and go to the second beam, and these things are called blades. They come to the second one, and then they can interfere again, and they interfere in such a way that we can set it up so that only one detector will detect the neutron going through. I think I have a little animation. Oh, good, you can see it. So the neutrons are coming here. They split in two. They are at two positions at the same time. They come back, and it is set up so that if there's nothing in the interferometer, only this is going to click. Only this detector at the bottom. Now, we want to use this, not only to look at the fact that you can neutrons can be at two places, but we're going to put a small piece of material. And what the small piece of material does is that it slows down the neutrons. It changes what we call the phase of the neutron. And suddenly when they come back and kind of re-interfere here, then suddenly they come back here, and some come down, some go up. So both detectors will detect with a certain probability. And this gives you an idea of what has the neutron has seen, what has gone through that material. And as you move this material a little bit, you can use it to image that material. Very similar to what magnetic resonance imaging, or MRI, is doing, but in a different type of way and system. Now, if the wavelength of the neutron is nanometer, size of atom, and you have an interferometer which is this size, you can imagine how fragile it is. If my hands move by 1 nanometer or shakes by 1 nanometer, then the interference pattern that I see here is going to get destroyed. And indeed, it is very fragile. In real experiments, this neutron interferometer is put on what is called an optical table, which takes care of some of the vibration, first step of isolation. Then it's put on a big piece of concrete, which weighs about 30 tons. So all the low vibration can get damped. The optical table takes care of high vibration, the piece of concrete, the low vibration. And then you don't want to have any thermal gradients. So you put this in a room which is well isolated for temperature. And the room is about half of the size of the stage here. And then you don't want to have any acoustic vibration also. So you put this in another room, and all of this, so that you can image that piece of material. I mentioned quantum error correction before. And it turns out that although neutron interferometry is not new, it's 30, 40 years old, nobody had thought about how to make them robust against the noise. We found quantum error correction, which guided us about how to make these systems robust. I won't go into very much detail, but just to tell you, by changing the shape of the interferometer, instead of making go only one path here, it will go up here and then cross around here and the other way around. And this makes it robust to vibration, which works this way. Because the path in here gets longer when it rotates this way, but it gets shorter in here and longer. And if these things are kind of well matched, this cancels. So by doing this, we can make a small quantum sensor which becomes much more robust, which has been kind of inspired by quantum information science. So this is the path of this, and you see a cancellation. You can think about the cancellation of the length of these paths if you are rotating around the axis perpendicular to the interferometer. If you don't use these systems, but someone like this is what you should see. And this is what you really see in reality. Okay? So the interference pattern that you see, the oscillation disappears. When you use the new improved interferometer, then you can see that the experiments with the vibration and a nut gets canceled with each other. So here's one example of a quantum sensor. I have other ones, anybody is interested to come, a small piece of diamonds where we have artificial atoms in them, small piece of superconducting materials, which makes a small magnet being very sensitive to magnetic fields, and more of those. Quantum sensors are things which are happening today. These systems are being commercialized at present, and companies are starting to use them for different types of applications. Quantum key distribution that I mentioned is something which is going to happen in the next 5 to 10 years. Quantum computation will see some with 100 quantum bits in 5 years, but to get to 1,000 to 10,000, we'll see something in 10 to 20 years from now. So that's the time scale that we're talking about. I'd like to finish by coming back to that circle. The work in quantum information science was really motivated by curiosity. That's really what brought this to people. Curiosity to try to understand properties of nature, properties of quantum world. We are present in quantum information science in trying to control this quantum system and try to scale it up and start to develop technology. In the years to come, we'll start to see the social impact of them and where it helps us in many places around the world, that it be medical application, can be trying to look at natural resources extraction, and then building new devices to push our curiosity in different ways. And I'd like to finish by thanking my colleagues at the Perimeter Institute, the Institute for Quantum Computing, and Quantum Valley Investment, this group in Waterloo, who are really pushing to develop these quantum technologies from the fundamental question of what does it mean to be in superposition? Can really larger systems can be in such state? To the application of this and development of the experimental part of us, to venture capital to take these things out of the lab and bring this to all of us. And finally, thanks to Mike Lazarides, who has funded these 3 organizations, the Government of Canada and Ontario. Thank you very much.
Very good. So Ray has very kindly agreed to take questions from the floor, and there are microphones, so do we have any questions?
Could you comment on the D-Wave system, please?
So this is a common question that I have. D-Wave is a company in British Columbia who has claimed to have a quantum computer. Now, when I mentioned a quantum computer, I gave you what are the ingredients to build a quantum computer. And one of them was to have a set of gates which are universal, which means that any programs can be built out of this particular device and these particular operations. D-Wave has tried to build a quantum computer of that form in the beginning of the year 2000 to 2005. But it turns out that they did not have sufficient control and their quantum bits were too noisy. So they decided to try a different approach. Instead of thinking about the essential ingredient is to be in superposition of all these quantum states, they used the tunneling idea. And so what they build is not a quantum computer, as I mentioned it, but something which is called a quantum annealing device. They will make a state of a quantum system, and they are hoping that the tunneling of quantum mechanics is going to bring the state to the ground state of a system. And you can translate any problems that you're interested in into finding the ground state of a certain quantum system. Now, they are limited. They cannot find the ground state of any system, but only a class of them. And they are hoping that their particular device is going to do this. So we do not know if this particular strategy, we do not know in theory, if there's really an advantage of doing this. That's the number one, that comment on D-Wave. The number two is their quantum bits cannot be in superposition of 0 and 1 for very long. So they lose their quantumness very rapidly on time shorter than the time of this tunneling. So it seems to be hard that with the present devices that they have, they could have an advantage. But the complexity of the math to really prove or disprove this is incredibly hard from the theoretical point of view. So their approach is, let's try to build it and see what happens. From there, to claim that you have a quantum computer is quite a leap. Thank you.
More questions? Over there at the back.
Hi, yeah, I just wondered if it's possible to do this, I don't know if it is. What's the difference between entanglement and triple entanglement, which I've read about in Ansell's book?
So the question is, what is the difference between entanglement and triple entanglement? So I assume that many people have not read that book. So I'll explain a little bit some ideas of entanglement, which is not an easy concept to understand. We don't have a pictorial view of what entanglement is, but I'll try to explain to you what it is in some kind of form. Entanglement is a purely quantum property related to correlation between two different systems. So to understand this, you need to understand what are correlation. Suppose that you have a pair of socks in a basket, and they have been clearly put together. Then you'll have the blue ones match with the blue ones, and the green ones match with the blue ones. So if you take a pair, you'll see they match very well. So this is perfect correlation. If you ask a physicist to put these socks together, you'll quickly realize that they don't always match. So sometimes the blue ones will be with the green ones, and so the correlation is not perfect. So you can quantify how things are correlated with each other. You can make equalities of kind of how strong correlation can be. And if you can do this classically and say, if you do these kind of experiments, correlation have to be such that they obey this equality. You add this operation and do these experiments with different types of socks. The quantum socks turns out to be in red and blue at the same time. And it turns out that there are some operation you can do in experiment, and it's called Bell experiments, which shows that you can have correlation which are stronger than what you can see classically. And part of quantum information science is to use these resources of these new type of correlation to do something. I mentioned quantum teleportation, which I did not explain it in any detail, but you use entanglement to be able to move correlation from one place to the other. And it turns out it is very powerful what you can do with these entangled states. Quantum key distribution, the way I explain it, of two photons going to one place to the other, I did explain exactly how you were doing all the measurements, but if you have no entanglement, then you could find a way to detect without being seen. But with entanglement, the eavesdropper, Eve, cannot learn something about that state without having an effect on it. Now, the entanglement has this property that it is monogamous. You can be entangled only with one person. With certain class of society, they have used this to justify why we should only be married to one person, because quantum mechanics tells us. So it turns out if we have a third party, you can have then Alice and Bob, if they want to be entangled with Charlie, then they have to reduce the entanglement with each other. So there is a different type of entanglement when you're three and you have two. The more party that you have, if you look at only a subset of it, the less and less entanglement this subset has. So the quantum mechanics kind of keeps this relation between the two. Yeah? So I think it explained a little bit about the difference between two-party entanglement, so you can be fully entangled, but with three, you cannot be fully entangled pairwise. Now, there are states which have entanglement with three states. They are called the Greenberger, Horn, Zeilinger states. So they are corresponding to having 0, 0, 0 plus 1, 1, 1 for quantum bits. And the other state we were thinking about 0, 0 plus 1, 1. So slightly different type of entanglement.
Well, I think we've probably come to the end of our allotted time. I think this has been an absolutely wonderful lecture. You've shown us a wonderful vision of the future, and I think the message of the incredible places you can go with this curiosity-driven research is a very appropriate message for the Andrew Chamblin lecture. So for all this, thank you once again.